Assalamu alaikum. This is the complex engineering problem of ground control engineering. My name is Muhammad Faizan Khalik and my group member name is Imadul Hasanawan. First, this is the problem statement. This problem is related to Kalabagh salt mine. The mine is experiencing issues of pillar failure and flooding. Kalabagh is located at the western bank of Indus River district Miyawali. While Kalabagh salt mine are located on the bank of Indus River. Salt is excavated by using room and pillar mining method where the salt is still mined manually. Let's talk about the stratigraphy. The salt ridge formation is belong to Precambrian age. Salt ridge formation is divided into three different members: Sahiwal marl member, Bandar Kes gypsum member, and Bilamwala salt member. Rock mass properties. Following are the properties that are required in this report, which include unit weight, Poisson ratio, UCS, Young modulus, and GSI. The company is not willing to spend money on the rock testing in the laboratory, so another way to find the rock salt properties is from the article and research papers that are present on the internet. These are the gypsum properties as you can see in the table, and these are the marl properties, and these are the rock salt properties that we get from the different papers and articles that are available on the internet. Rock mass properties can be calculated using RockLab software. These are the results that we get from RockLab softwares. Design of opening. Stresses around horizon. First we have the vertical stresses. Vertical stresses can be calculated as the given relationship, and horizontal stresses can be calculated as the given equation. First calculate the vertical stresses. Vertical stresses for the best case scenario. For best case scenario we have our burden of two rocks, gypsum and marl. First we calculated the unit weight using weighted average formula, and vertical stress is calculated as 3.68 megapascal. For worst case scenario we have our burden of three rocks, gypsum, marl and rock salt, and vertical stress is calculated as 5.82 megapascal. Now for horizontal stress, the value of K is in the range. So for best case scenario we have two values of K, and horizontal stress is 3.49 megapascal and 41.731 megapascal. For best case scenario we have the values of horizontal stress is 4.59 megapascal and 51.85 megapascal. Shape of opening. Designing of mine shape is very critical work. There are many shapes: circular, rectangular, arch and horseshoe. Among different shapes of mine opening, that shape is chosen which is most suitable in terms of stresses. Arch shape is suggested with respect to the above parameters like stability, appearance and diverting stresses. Size of opening. As size is shown in this picture is the most suitable cross-section design for the mine opening. Height of mine will be 4 meter and width will be also 4 meter. Stresses around adit. Stresses around the adit were calculated using Cringe equation. Tangential, radial normal and shear stress on the roof and wall were calculated using these formulas. For the best case scenario, stresses in roof. Tangential stress is 6.82 megapascal. Radial stress is 0.179 megapascal and shear stress is 0 megapascal. Stresses in wall. Tangential stress is 7.54 megapascal. Radial is 0.179 megapascal and shear stress is 0 megapascal. For the worst case scenario, stresses in roof. Tangential is 145 megapascal and normal and radial normal is minus 227.59 megapascal and shear stress is 0. Stresses in the walls. Tangential stress is minus 34.36 33 megapascal, and radial normal is minus 2 to 7.59 megapascal, and shear stress is 0 megapascal. Factor of safety. Factor of safety can be calculated by UCS divided by hoop stresses. For best case scenario, we have the our burden of 2 rock, gypsum and marl. We calculated the UCS using weighted average formula and put in the factor of safety formula. Factor of safety is 4.378, which is greater than 1, which means for the best case mine is safe. For the worst case scenario, we have our burden of 3 rocks, gypsum, marl and rock salt. In this case, factor of safety is 0.178, which means the mine is not safe in the worst case scenario. Now the stability analysis. In this report, we are using phase 2D for stability analysis. The final design of mine is verified using phase 2D software. In this software, we made the design without support and checked the validity of design. Without support, it shows the area with high stresses, but we can apply the support to stabilize the mine and there will be no failure.
After stability assessment of mine opening, pillars are designed. For designing the pillar, factor of safety of pillar is selected first. This is the formula of factor of safety where sigma p is stresses on pillars. We have defined 1.2 value for our mine pillars. By putting the values in formula, we get sigma p is equal to 14.17 megapascals. For designing pillar dimensions, this formula is used where sigma p is stresses on pillars, PZZ is vertical stress, WO is width of opening and WP is width of pillar. Putting the values in formula, we get width of pillar is equal to 4.17 meters. We choose 4.2 meter for our mine. Recovery ratio. It is defined as the ratio of mineral extracted to the mineralable reserve in a deposit. Putting the values of width of opening and width of pillar in this formula, we get recovery ratio 48.78%. Next section is ground control. Hazards of flooding. Groundwater is one of the major hazards in mines. It can cause different problems in ground floor. If one level of mine is flooded, it will cause following hazards. Formation of cavities. Water can enter in cracks, fissures, and fractures and form cavities which further weaks the rocks. Groundwater can also increase the temperature of mines, which will increase the humidity of mine environment. It can also cause subsidence in mining due to leakages of water in mine level. Pillar failures. In shear pillar failure, a crack is produced in the pillar. It is a UCS type failure and can be formed by inclined beds of formation. In concave pillar failure, stresses increases slowly and causes chipping in pillar. Chipping will be maximum at center and reduces at corners. In convex pillar failure, internally vertical cracks are produced due to high stress, which splits the pillar internally and cause swelling in the pillar. Following are the engineering solution of pillar failures. To avoid pillar failure, we can over-design the pillar, we can also change the dimensions of pillar, we can relocate the pillar layout, we can change the stress distribution of pillar. And these are the conclusions. Rock mass properties are gathered by literature. Vertical and horizontal stresses are calculated for both best and worst case scenario. Stresses around the edge are computed by Kirsch equation. Arc shape is selected for mine opening. Factor of safety is calculated for both best and worst case scenarios. Stability assessment is done by phase 2D software. With help of factor of safety, pillar dimensions are defined. Ground control hazard due to mine flooding are discussed. And at the end, engineering solutions of pillar failures are given.